So when I see something like the first problem, and so these are in order, it's 1 through 7, and then we'll switch over and do 8, 9, and 10 directly on Blackboard. But so for this, we could do it algebraically. We could also do it using Desmos. Right, so it's really up to you. I'll show you the algebraic approach because I know there are plenty of folks who like that approach, and then I'll show you Desmos. All right, so if you're using algebraic approach, first thing you do, or analytic approach, what it's properly called, you replace each x value with the limiting constant, in this case of 2. You get 1 over 2 minus 1 over 2 over 2 minus 2, and that's indeterminate, which means that there's a limit to be found. It's just you have to do some algebra to get there. All right, so I'm going to rewrite my limit as x approaches 2, 1 over x minus 1/2 over the x minus 2. All right, I'm going to get a common denominator by multiplying this fraction by 2 and this fraction by x. So the limit as x approaches 2 of 2 over 2x minus x over 2x over x minus 2, which gives the limit as x approaches 2 of 2 minus x over 2x over x minus 2, which I'm now actually going to write over a 1. Oops. So that I can kind of remind myself where that x minus 2 is going to go when I multiply by the reciprocal. All right. So limit as x approaches 2, 2 minus x over 2x times x minus 2. All right. Now these two expressions are opposites of one another. All right. If you're ever unsure of something like that, Desmos is a really reliable friend. Tends to stick with you through thick and thin. If you're not sure, type the expression in 2 minus x, x minus 2, and you'll see that the result is always a result of -1. All right, that y value is always a -1, or it's constant. Right? If you don't like that, because if you're doing it algebraically, it might be because you really don't like that most. You have a common factor of -1 that can be taken out on top, which gives you an x minus 2 as a result. And you have your 2x and x minus 2. Those x minus 2's would cancel. Now I can do my resubstitution into the simpler expression and get my result of -1 over 2 times 2, which would be -1/4. Choice B. So, you can do it that way. You could also type in your original expression. Right, y equals f of x equals however you like. Now we're looking at 1 over x minus 1/2. So another fraction, 1 over x minus 1 over 2 x minus 2. All right, that's what our expression yields in terms of a function. As I approach the x value of 2, so I'll pop in an x equals 2. Make it dashed. I want to know where the graph is approaching. Right? As I come in from the left and I come in from the right, I'm going to the same location. The problem is that same location come on, get on there. Kind of messing with me now. well, we'll say is undefined, or it's an open circle anyway. Come on. All right, well, let me bring it in, see if I can get it that way. I had it, there you go. It says undefined, right? It's not really undefined, it's more like indeterminate, but it's an open circle. But that open circle does have a y value. You can figure out what that y value is, you'd be in good shape. Now, I know it's kind of hard to see, but on the left-hand side, you see a negative 0.2 and a negative 0.4. There is a scale there, all right? Every 2 boxes is 1/10 of a unit, right? So if you know that 2 boxes down from the negative 0.2 is going to get you to a negative 0.3, split the difference, that'll get you to this location, which is going to be negative 0.25. However, I think it's probably borderline common sense that as you're going through and you're like, okay, what value is this approaching? I'm not 100% sure, but it sure does seem to be closing in on negative 0.25, at least before it goes to undefined. Okay, so you could pick it out that way too. Right. You could also go with a table approach. Right. So if you, oh, that one nuts. If you hit on that little wrench, then tap on the table, it'll tell you where the undefined values are. The problem with this is if it's a funky decimal value, or there's a major change between the consecutive integers around it, like I've narrowed it down. It's somewhere between negative 0.5 and negative 0.16 repeated. It's like, okay, well, that doesn't help. So then I would say, okay, well, let's see what's happening. If it'll let me at 1.999999, something really close to 2. It seems to be closing in on negative 0.25, throw in an extra 9, and they'll kind of lock in and say, it's basically saying I give up. It's saying uncle at this point. You put in enough 9s, it'll just tell you what you want to know. Right, so it's kind of a nice feature. Right, so same idea for number 2. Although there is an algebraic approach, you can still use Desmos. If you want to use the analytic approach, rad 4 minus 2 over 4 minus 4 gives you 0 over 0. That's an indication that there is an answer to be had. You just got to do the work to get it. So limit as x approaches 4 of rad x minus 2 over x plus 4. There's a few different ways to handle this one. One way, and probably the simplest way, is to multiply by a conjugate. All right, so multiply top and bottom by radical x plus 2. All right, when you distribute out the top,
It's x minus 4, right?
thank you. Much appreciated. When you distribute out the top, rad x times rad x is going to give you an x. The outers and inners are going to cancel, leaving you with a minus 4 when you multiply the negative 2 by the positive 2, which is beautiful because I have an x minus 4 on the bottom that's just dying to be canceled away. So boom, boom. Numerator cancels to a 1 over the root of x plus 2. So 1 over the root of 4 plus 2. So 1 over 2 plus 2, also known as 1/4. All right. Same idea as far as Desmos is concerned. Just going to refresh here. I did a little Zoom business here and I'm paying the price. Okay. So original function, y equals fraction, radical x, pull it out, minus 2, x minus 4. We want to see what's going on around 4. right, so I'll type in x equals 4, just a visual aid. That whole thing about making it dash, it just makes it pop a little bit. All right, so then I look at it, I get really close. At that location, I see it goes undefined by Desmos's way of thinking, right? But it's not really undefined, it's indeterminate. As I get closer and closer, as I move in from the left, it appears to get closer and closer to 0.25. From the right, it appears to be increasing towards 0.25. So it's reasonable to assume that you're going to get to 0.25. However, you could also go to the table approach and say, we know we're living around 4. So pop in a 4, it says undefined. Pop in a 3.9999999. Maybe you even go like 4.00001, something like that. Maybe a few more zeros, just to see what's happening a little bit south of 4 and a little bit north of 4. You see it's living around 0.25, so it's logical to assume that at that hole we would be looking at a y value of 0.25, right? Otherwise known as a quarter. 1 quarter. All right. So number 3, limit as x approaches 3, same deal. We want to look to see, again, because it is possible, and maybe you just got to substitute in. However, if you put in a 3 on the bottom, it's going to go to 0. Just a question of, will the top go to 0 also? So we give it a look. All right, 9 minus 24 is negative 15 plus 15 is 0. So 0 over 0. That means math can happen here. Algebra to allow us to simplify. The numerator factors to x minus 3, x minus 5. Kind of cheated there a little bit. Not in the sense that I knew what the answer was, but in the sense that if I knew something was going to cancel, well, one of the factors would have to be x minus 3. So the other one had to be x minus 5, because negative 3 times negative 5 would give me the positive 15 that I need. So, little things like that. So I got through all my math classes. No, it's just mathematical intuition. It's a number sense is what they call it. Right. So it takes a little doing, but you get there. You're not already there. Probably already ahead of me. Okay, so x minus 5 over x minus 3. Now I plug in my 3. I'd have 3 minus 5, 3 minus 3, and this is the rut row situation, because I look at it, I say negative 2 over 0. And so that means one of 2 possibilities. One possibility is that it's a DNE, but don't just go for DNE because you see undefined. Right? It could be the case that it's infinity. If it's undefined, it could be because there's a vertical asymptote. If the curves are going to the same, or going in the same direction, going to the same infinity around that vertical asymptote, then your limit could be infinity. So we can't jump to conclusions here. Right? But what this tells us, unless you want to get into numerical testing and all that stuff, is that you probably want to default to a graphical approach. All right, so y equals x squared minus 8x plus 15 over x minus 3 quantity squared. Now we got this little bit of funny business going on over here. That's just Desmos going a little wacky. Right, so it's kind of hard to see, but you got a curve there. It just makes it seem like it comes to a point, although it just isn't, so. But what we would do here is investigate. I would go by points just to see what's happening. But even though in this case we have a removable factor, a factor that seems to be consistent with a removable discontinuity, it also happens to coincide with a vertical asymptote. All right, so going by the points here, around 3 gives us the undefined, you know, in Desmos speak, we know it's really indeterminate. So let's get 2.999, yep, 99999. That seems to be pretty big. And then 3.0000, and then throw a 1 and see where that's going. I kind of overdid it with my zeros here. Oh, there we go. One of them's going up to infinity. The other's going to negative infinity. All right, really big numbers, but one of them's positive, one of them's negative. All right, that's probably what you suspected, but the nature of the funky graph kind of throws you for a loop a little bit, so you don't want to take the chance. All right, so this one, because we have a disagreement, it's a DNE, and that is because the limit as x approaches 3 from the left of this whole function, I'll just call it f of x, is equal to infinity. And that's because this one goes up forever. Right, this piece here. The limit as x approaches 3 from the right of f of x is negative infinity. And that's because this piece goes down forever, even though it loops back part of it upon itself. It does go down forever. We would say the limit does not exist. Therefore, the limit as x approaches 3 overall of that given original function is DNE. All right, so the analysis is multi-level here. So this is one of the trickier types of situations because, you know, I know a lot of people kind of fall in love with one approach as opposed to another. I'll just do it this way. I'll just do it that way. But you're really on the hook for both techniques to some extent. All right.
Can you go up to number 2 quickly?
Say it again?
Go to number 2 just really quickly.
One more time. Sorry, I couldn't hear.
Number 2.
Number 2?
Yeah. Oh, all right.
All right, good.
Yeah, thank you.
No problem. All right, so number 4, for the function given, find the slope of the secant line over the domain. All right, so the slope of the secant line, very easy to compute if you're given a particular domain. All right, that's a good thing. Like, you don't want to have to reinvent the wheel every time, as they say. So you can just Desmos it up and call it a day. Right. So in Blackboard, I gave you a Desmos called difference quotients. Right. And I put a dummy function here just to have something that won't give an error. But if you type in your given function and then the interval, right? The lower bound is A, the upper bound is B. All I'm looking for a question like this is an answer. If you want to do it out by hand, by all means, go for it. I wouldn't, because all you would need to do is slide your slider to your A value, slide your second slider to your B value, and then look down below and see what your result is going to be. Slope of the secant line is f of A plus h minus f of A over h, or f of B minus f of A over B minus A. In this case, it's this one that makes more sense because you're given A's and B's. All right. So Desmos will tell us, you just tap on that little fraction icon to get a clean answer. Slope of the secant line is negative 1 over 18. And that's all she wrote, whoever she is. Right. You would not need to show any work of a manual nature on the test. If it's a free response question, you know, not a multiple choice where it says, show your work in the blank or whatever, just put the Desmos link in, all right? But just remember, in order to share your own Desmos work, you have to have an account. So you got to create your account if you haven't already done so, and then create the share link. So just a quick review on that. You see, it says my name on the top, Theodore. Right? So I have an account. My account is created. So you open one of my Desmos links, you jimmy it up, and you get all your stuff in there, and it looks great. And it's just the way you want it to look on the test. So then you'd hit save. You tap on that save button there, and then tap on the share link. Share this link. Don't mind if I do. Copy that bad boy, and then just pop that right into Blackboard, right, as part of your solution, right? So that's what I meant by, like, some of them are so easy that it's like, oh, that's all I gotta do. Sometimes just looking for the answer, you know, that's a possibility. Now this one, find the slope of the tangent line using the limit definition. This is the counterbalance to that, right? Where the other one, we didn't have to do much work. This one, you have to do all the work, right? So find the slope of the tangent line, another term for derivative. But using the limit definition, all right? So you can pick your poison over which form you want to use, but the one we were using in class was the limit as h approaches 0 of f of x plus h minus f of x all over h. We already have the f of x part. We need the f of x plus h, which we learned previously is the same as saying, all right, take your original function, replace every x with an x plus h. So that part is not going to be too bad. Everything that happens after that makes you understand why there are some easy questions on the test. So 2 parentheses x plus h to the 1/3 minus your original function 2x to the 1/3 all over h. Okay. Now, these limit definition questions are at heart, or at their core, they're essentially proofs, right? So there's no skipping steps on these, right? And what I mean by that is we learned some shortcut rules, and those shortcut rules are fabulous. They do a great thing for us. They save us time and energy. They keep us from having to waste brain power trying to figure out solutions to things when we already know the answer. So it is absolutely wonderful that you already know the answer to this is 2/3 x to the negative 2/3 power. You need to prove it to me using the limit definition to get the credit. All right. That's what this question is asking us to do, which means that you got to go through this process. So we have a common 2. I'm going to pull that out. We have the x plus h left over. That 2 is irrelevant to the limit. It doesn't have an h attached to it. I'd love to be able to get all the x's out too, but there's no common factor of an x, so I'm kind of stuck with that stuff. All right. So we talked about, it had to be 3 classes ago by now, maybe 2 classes ago, the sum and difference rules for cubes. You know, sum of 2 cubes and difference of 2 cubes. And in this case, we apply the difference of 2 cubes rule. So I'll just write the rule again here. The difference of two cubes. I had a brain cramp there. I almost said 3 cubes. That is a different story altogether. Okay. So it's a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. All right. So what we're doing is we're letting a be equal to x plus h, and b is going to be equal to x. And then we just fill out this whole formula with that information. All right. So when I'm chuckling there, it's not like because I find it funny. It's more like chuckling with incredulity. Right? So it's like, ah, no way. Yeah, way. We got to do that. Right? So it would be x plus h cubed minus. Oh, you know what? Sorry. I forgot the power of 1/3, like a schlemiel. Like as in what I have written right here. And I'm looking at it, I'm like, why is this about to get like impossible to do? So plugging it in, we'd have x plus h to the 1/3. But then since this is cubed, we'd say cubed minus x to the 1/3 cubed, which simplifies, and we kind of did, we sort of, I don't want to say glossed over it, but we did it a little bit quicker last time. This becomes x plus h minus x, which simplifies down to h. Right, so that's the left-hand side. And at the right-hand side, we're going to have a minus b. So we know our a, we know our b. All right. And then we just have to take care of this piece and then start the substitution process. You just got to kind of shrink it down and clean it up a little bit. All right. So a squared. So our a is again the x plus h to the 1/3. That's getting squared plus a times b. I'm just going to write it down here and then put it all together in a second. X to the 1/3, x plus h to the 1/3, and then plus b squared, which would be I'm going to use brackets here and close it up. X to the 1/3 squared. Okay, so like I said, I'm just cleaning it up a little bit, put it all together in a way that hopefully it'll make a little bit more sense. I just got a lot more shrinking. There we go. A little bit better. All right, so we can clean up just a little bit. There isn't really much to clean up on the right-hand side. It's kind of ugly. It really is just a matter of saying, all right, well, the 1/3 times the 2 gives me a 2/3. Right, so that's in both cases over here, but everything else is going to stay pretty much the same. There's really not much else I can do. All right, so, it's kind of like, don't lose sight of this expansion because this is pretty helpful. Otherwise, you have to reinvent this wheel, right? So all of this, when multiplied together, will end up giving you an H. It's just we needed the expansion so that we could say, all right, we have our limit, this whole thing here. If I multiply it by this, top and bottom, make sure you do it both places. Then it's going to help us simplify things. That's really the idea, right? But in the case of the numerator, it's really going to simplify things because we know, again, that the binomial multiplied by the trinomial is going to clean up to just an H. So this is going to become H over H multiplied by this whole mess. But now those H's are going to cancel away. I mean, we still got the limit and the coefficient of 2, but that's not what makes this difficult. This stuff here, it's this beast. We can get rid of that. We'll be in good shape. The H's cancel to a 1, and now I can make my substitutions. All right, every H gets replaced with a 0, so I'd be looking at 2 times. I have 1 over x plus 0 to the 2/3, so x to the 2/3, plus x to the 1/3 times x plus 0 to the 1/3, plus x to the 2/3. All right, it's 3 of the same thing. Right, because these two pieces together multiply to give you x to the 2/3. So I have 1, 2, 3 x to the 2/3, and so 2 times 1 over 3 x to the 2/3 would at long last give me my derivative f prime of x, 2 over 3x to the 2/3, which is equivalent to 2/3 x to the negative 2/3, which is what you would have got with the power rule, which is incredibly infuriating if I were a student. But yeah, it's a rite of passage. Right? We all have to do it. You're going to demonstrate knowledge and skill associated with the limit definition. It will come back repeatedly in your calculus careers. Again, if this is your last stop in your mathematical journey, yeah, no, it won't come back again. But yeah, that's part of the fun, I guess. All right, so a lot of stuff in this question, but not so much in some of the others. So it all balances itself out. So number 6, speaking of balancing, any question that involves numerical values, you do not need to do by hand. All right, it's a rule. It's a rule for me. All right. So if it's a derivative at a point, at a particular point, if it's a slope at a point, if it's a limit at a point, I'm trying to get rid of all this stuff here. Hold on. New blank graph. You don't have to do it by hand. Calculator work is all I need. And I think I probably proved to you why with the last question. It's the idea of like, I'm getting you with the by hand stuff. You don't need to do even more by hand stuff. I'm already getting you with that. All right. So what you would do for number 6, very, very simple. You type in f of x. And to answer the question that's definitely on somebody's mind, what if you asked us to show our work? Same thing you would do with the other question where you use Desmos and I ask you to show your work. Submit the Desmos link. All right. So here's my original function. By the way, if you ever wondered what it looked like if you multiplied a cosine and a sine function where one of them had a frequency of 2, the mystery is solved. All right. F prime of pi over 3. F prime pi over 3. Oops. Just do it without the oops and you're good. Negative 1.25. Oh, that's not a choice. Okay, hit the fraction icon. Negative 5/4. Boom. Take it and run. All right. So take it and run and enjoy the process. That's all I'm asking you to do. All right. For this kind of question, nothing more than Desmos work. All right. If I ask you to find the equation of a tangent line at a point, emphasis on the at a point, the Desmos work is fine. All right. You don't need to do anything more than that. All right. That's why I've been showing all these Desmos tricks throughout the semester. I mean, we're only a month in, but still, it's like, man, this guy really goes crazy with the Desmos stuff. There's a reason for that. It's so that you can learn how to use Desmos so that you can also use it on a test. All right. There's a reason. Part of the fun. Because I make up for it with a question like this. State the derivative of, now you see this is a function within a function, right? So this is a chain rule situation, but I got a little silly here and I put an extra link to the chain. So let me show you how this works. Like I was saying before, we didn't really have to do too much in the notes because I was going to show you one in the practice test. So we have f of x is equal to 3 times the sine of 3x raised to the second power. Oh, I wrote f of x. I'm going to write this as y equals just for convenience. So we'll say y equals 3 sine 3x squared. All right. So when we're applying the chain rule, we want to take the more complicated part of the interior of an expression and pull it out so that what remains is something that would be simple power rule. All right. So I would ask myself, what would happen if I replace that sine of 3x with just a u? So off on the side, I'll take note of that. I'll say, let's let u be equal to the sine of 3x. Right? If I did that, I would get y equals 3u squared. That's beautiful. This is what I want. It's power rule ready. All right. This other piece is not, well, it wouldn't be power rule anyway, but it's not rule ready. Right? Because we know the derivative of sine is cosine, but we haven't talked about, okay, well, what about if it's sine of 3x? I mean, there are shortcut rules for that kind of thing too, but you could also pretend that this is a brand new problem and say, all right, forget about the, I'm just going to get a little silly here. Screenshot. Copy. All right, so pretend this stuff isn't here. All right, nothing there, nothing to see here. All right. Pretend that this is its own problem. And you want it to use the chain rule. I'd look at it and say, you know, this would be really easy if only that 3x wasn't there. So let me make up a variable. I mean, I already used u. So I'll just go the next letter down the alphabet. So I'll say, let's let v be equal to 3x. Okay. If that's the case, then I would call this u equals the sine of v. All right. Now, unfortunately, we really did actually have more to it than that. We had the 3u squared, but now we're looking at something that involves three pieces, where if I composed it all together, if I took the 3 and put it in for v here, and then took the sine of 3x and put it in for u there, I would get back to where I started. All right. All we're doing is literally unpacking the expression. All right. Then we take the derivative of each part, dy, du, du, dv, looking at independent versus dependent variables, dv, dx. All of which are either power rule or basic rules. 3u squared, derivative 6u. Sine of v, derivative cosine of v. Derivative of 3x, 3. All right. The extra twist on this is what would happen, or what would I have to do? Oh, nice. What would I have to do if I wanted to get dy dx? Well, looking at the three different pieces here, again, I have a dy du, a du dv, and a dv dx. If you were to multiply all three of these things together, you'd see that the du's would cancel and the dv's would cancel, and you'd be left with just a dy dx, which is ultimately what we're looking for, dy dx. All right, so what that's telling me to do is take my answer for dy du, multiply it by my answer for du dv, and multiply that by my answer for dv dx. And the result is going to be equal to dy dx. The only thing that would remain, because all the derivative taking is done, is making some substitutions. All right, so we know u is equal to the sine of 3x. We know v is equal to 3x. Everything I need for a substitution is on paper. It's right in front of me. So 6 sine 3x times cosine of 3x times 3 would be equal to my derivative. Right. So it's got that extra layer to it, but it doesn't make it any more complicated in terms of finding the derivative. It's just an extra piece that you have to keep track of. All right. So that was number 7. We're going to hop over or hop back to the